All right, let's just get started. Well, hi everyone. Welcome to the February meeting of the Ottawa Centre of the Royal Astronomical Society of Canada. My name is Mike Mogadam. We've got a wonderful evening here after a few technical glitches. Tim, I'm going to have to ask you to advance it one slide, please.
Oh, patience, patience.
Hopefully we'll get these things ironed out.
Everybody's a critic.
Doing great, Tim.
All right, terrific. So, usual program, we've some exciting additions. Gary and Al will speaking to Ottawa Skies this month, plus the astronomy news, as they usually do. Thank you. Very special guest tonight, and Monica Ferguson, who's a map specialist at Carleton University. She's here tonight to share some maps of the cosmos, and I really appreciate her doing that. I always marvel at people who can, they bring their day job, after hours and willing to share it with people. That's I very much appreciate that. Then we're going to have a break, and followed by a couple of other interesting presentations. Frank Marshall, who I think you may have seen in my agendas. He's a master's student, physics student at Carleton, with a passion for the Martian astronomy, Mars Curiosity rover, and all the instrumentation on it and the mission objectives. I've seen his slides. It's quite impressive. And Glenn Ledrew, well, everyone knows Glenn Ledrew. You can be sure that you're going to be learning something from his, all about stellar associations of Perseus. Okay, next slide, please. Okay, so and John Dobson, I'm sure many of you have heard, he died recently after 99 years. It's incredible. Many of you know him as the father of sidewalk astronomy. He brought low-cost astronomy to everyone with inventing the Dobsonian telescope. Some facts that you may or may not know. He spent 23 years in a monastery, and his mission was to really try and reconcile some of the Eastern faiths with Western science ideas. And in that time, when he was reviewing that, he started to look at the stars and came up with the Dobsonian telescope. Deep passion for astronomy and sharing it, and hence the name Sidewalk Astronomy. So sad to see him go. Looks like he had a full life, though. Next slide. Okay, one thing I really enjoy doing here, and it's not too loud for him, are you? Okay, terrific. If it is, let me know. Welcoming new members. So these are people who recently joined our group, and I always like to welcome them. So Peter Geldart, are you here tonight? If you are, raise your hand and arm and okay. Andrea Lobel, Alan Lyons, Yasmin Miguel, are you here tonight? Okay, well, welcome. I'm glad you could join. If you are here, and please come say hi, and most importantly, in the break, as we had last month, we'll show a slide which we'll leave on there, and it'll show some of the benefits of membership. Okay, some things you may or may not be aware of. So thanks again. Next slide. All right, members in the news. Okay, so this is from the February edition or the February RASC calendar. Deborah and Peter Sarvolo, who are often in the calendar. Omega Centauri, and the usual fine word from them. Next slide. Also here is Trevor. Okay, their son. This is a shot from in the bottom or on the left side there of the Okanagan, sort of with the stellar trails. So he's sort of carrying on the tradition of his parents, obviously. From this is from the Sky News that just came out. Next slide. Gary Boyle. Okay, you may remember there's always talk about some of the auroras. Well, this is a shot that Gary took a while ago, a very spectacular one. It's a nice work, Gary. And this was in the Montreal Gazette. I think it was before January 9th. So nice work, Gary.
So I got on air to let everyone know the aurora is probably going to be coming. Then I have to go on air next day to apologize the aurora didn't come. So it was kind of a letdown because with the extra solar flare, you really expected one of those, and it just didn't materialize.
Yeah, it missed us a bit.
Just a bit.
Okay. Gary, over to you. I know I'm Russian, folks, but there's some really good presentations, and I think I want you to hear less of me and more of them.
You're Russian, you're Canadian. Well, good evening again, folks. Welcome everybody here in Ottawa and in TV land on the internet for the Ottawa Skies for February 2014. Next slide, please. Well, first of all, starting around the 22nd of February, we'll be looking for these zodiacal lights in the western sky. Of course, you must be out in country skies, where I am, pretty well away from city lights. And really what it is the zodiacal lights are seen close to spring and close to fall, springtime in the west and the fall in the east. And pretty well it is just the debris of our solar system, the leftover dust pretty well. And we're seeing right along the plane. It's pretty faint, pretty hard to see, but once you spot it, you say, oh, there it is. So you probably have seen it if you're in the country during those two time periods, but maybe we'll get to see it sometime. And I did not take this shot.
I didn't get a chance to mention, I gave you another zodiacal light shot.
Oh,
From
excellent,
the same
excellent,
viewpoint.
excellent.
And you can really see there, it's on the plane of the solar system.
Yeah.
You've got Venus and Jupiter there.
There we go. Yeah, so it goes right along the plane of the solar system, along the ecliptic. Excellent. Thanks a lot, Tim.
And it's just about the same viewpoint as you had in the last one.
Excellent, perfect. So this month we'll just look at a few choice objects in Ursa Major, or the Big Dipper, as well known from school days. The first object will be here is M82 and M81. Next slide, please. Two beautiful galaxies, both about 12 million light years away. M82 is known as the Starburst Galaxy, or the cigar. No real name, I think, for M81. But
Bode's Galaxy.
which one?
Bode's
Oh,
Galaxy.
Bode's. Sorry, yes, Bode's. It escaped me. Sorry. M81 is a lot brighter. It's magnitude 6.9, and our eye can see naked eye to about 6th. But 82 is a little fainter. But the reason why I show those two, not just for the grandeur of these two objects, is for next slide. Is M82 actually has a supernova embedded in it. This was discovered on the night of January 21st in London, England. Very strange story to this. A school teacher was demonstrating a CCD camera to his students. So it was a semi-cloudy night, and so they decided to go up to the observatory to show how to work a CCD camera and just ask students, what object should we point the CCD camera at? So the teacher first put the object in the eyepiece, noticed that there was this dot that the experienced astronomer would know that it's not there, and then got it confirmed it's actually a supernova. The supernova now is about at its brightest at about 10.6. Now it's going to fade a bit, but this was a very, very large event for sure. For sure. In fact, people with good binoculars can almost see it just in binoculars.
I can't remember, what was the type? Type 1?
It's a type 1A, which is a dwarf dwarf star. Next slide, please. Our next object, it's M51, right at the very tip of the tail of a big bear. In mythology, here's the main part of the bear. We had the front paws, the back paws, the head's about up here, and then we had the very long tail. And I think it was Hercules that was, one of the hunters, I think it was Perseus, that actually took the bear and flung him into the sky, and that's how the tail got long. Mythology. I'm telling you, there must have been opium back in those days. To think of stories like that. So here we have right at the very end is M81, a beautiful galaxy. It's nicknamed the Whirlpool, and all the very favorite and well-known objects have nicknames to it. So the Whirlpool is 37 million light years away, and definitely a telescope to see it. And if you keep in mind that the moon is 30 arc minutes across, looking at the moon in the sky. In fact, if you put your pinky at arm's length, do not do it at a bus stop, people will just stay away from you, but your pinky nail is about the size of the full moon, and that's 30 arc minutes, and it's only 11, so about 1/3 of that. So just a beautiful galaxy to be seen, and it seems like the galaxy has a tail end to it, but it's just another galaxy, not really associated with it, but kind of disturbed by the main galaxy. Next slide, please. Yep. Okay, next we have is the duo of M108 and 97. Again, they fit pretty well in a nice wide angle field in your telescope or binoculars. Okay, next slide. We'll see a close-up of them. The M108 is a galaxy 45 million light years away. So it's amazing how far you can see, because people ask, how far can you see? Well, see galaxies pretty well before the dinosaurs were extinct on Earth. And it goes back, way back then, too. Again, a little smaller, and edge on, oops, I'll come back, no problem. And over here is called the Owl Nebula, M97. And it's a planetary nebula, which is the end of a star. Now, unlike the supernova that we saw in M82, stars like our sun will become just a red giant and just flake off its outer shells. The really gas cannot hold itself in anymore. And the owl, because we have these two little dark spots, it looks like an owl's eyes. Pretty elusive to see in a telescope. You need good conditions, good telescope. Again, it's almost 10th magnitude, but it's only 2,600 light years away. It's actually in our galaxy. Next slide, please. And we had a conjunction of two comets in the morning sky. In fact, here's Altair from the Summer Triangle. It's really great to get up in the morning as I'm leaving for 10 to 6 and see Cygnus in the east, and it's still minus 30. There's something wrong with that. So we actually have two, we have Comet Lovejoy and Comet Linear that are pretty well intersecting each other. The conjunction pretty well passed. You can see next slide. That is for tomorrow morning. Here's Lovejoy and Linear. So you can pretty well see them in one field of view. But Linear is a lot fainter than Lovejoy for sure. And these were taken from the Heavens Above website. So if you go to heavensabove.com, click on comets, and it'll show you specifically where the comet is now, or go in the future and see where it is. So if you've never seen a comet in your telescope, two shots in one. Next slide. And on the morning of the 24th and 25th of February, I took the shot last month at the end of January of the moon and Venus in the eastern sky. Venus is extremely bright. Who has never seen Venus? Anyone has seen Venus? Okay. If you look early in the morning sky, that's very, very bright object. At about 6 in the morning, that's the planet Venus. And so those two, again, will be close together. So your digital moment will be on the 24th or 25th. And next slide, I think that's about it. Just your favorite planets. Since Mercury moves so fast, it pretty well moves between Capricorn and Aquarius and back to Capricorn again as it moves into the nighttime sky. Venus, as we saw in the morning. Mars is getting ready for its apparition sometime this year. It's pretty bright in the sky. Jupiter is seen between the Gemini twins. Very, very easy to see, almost as bright as Venus. It's unmistakable, right up in the sky. Has some beautiful moons around it, and time to time, the moon's actually a cult in front of the planet. Saturn is, rising just before midnight, is out all night in Libra. And Uranus and Neptune, they don't move too fast. That's your thing. Next slide. And pick your February 24th. And it's the full snow moon. And then we have third quarter new moon, which is, in fact, this is the only month that we never had a new moon. The new moon before was in January, and the next new moon is actually March 1st. So we never actually had a new moon for February. And then back to, oops, that should be the other side. My mistake. It's when you do slides at 2 o'clock in the morning.
It just depends on the telescope.
That's right, yeah, it's inverted, yes, because the telescope will invert the image. Good comeback, Tim.
Anytime.
And of course, if you get on my monthly article, which is on rasc.ca, it's called The Sky this month, and I'm speaking about the part 2 about the winter Milky Way from pretty Riga down to the Big Dog, Ursa Major, and to Puppis. So although we had the Milky Way in summer, which is very prominent, we also do have a winter Milky Way, not as prominent, but it's still very nice to look at. And with that,
So the moon's really going to look like that, right?
like this, yes. After a couple of bottles of Chardonnay, I think it will. I think it will. Yes? Yes. Again, that's the 2 o'clock in the morning thing. Yeah, well, if you turn it upside down, it'll look like an R. Okay, sweet. If you're gonna do it wrong for the one small part of the slide. And this is it for next month, folks. More mistakes next month, I promise. Take care.
They're not mistakes, they're tests to see if you're awake.
Next slide. Okay, next up is Al Scott with the 10-minute astronomy news update. Al.
Good evening. You have the next slide, please. So I've got a couple news items for you. The first one is on formation of supermassive stars. Young massive stars, which have more than 10 times the mass of our sun, shine very brightly in the ultraviolet, and they heat the gas in the nebula around them. It's long been a mystery why the hot gas doesn't explode outwards and stop the process of star formation as soon as the nuclear fusion process in these high-mass stars kicks in. Now, observations made by a team of researchers using the Very Large Array Radio Observatory have confirmed predictions that as the gas cloud collapses, it forms dense filamentary structures that absorb the star's ultraviolet radiation as the star passes through them. And as a result, the nebula surrounding the star flickers like a candle over relatively short time periods. Stars form when huge clouds of gas collapse. Once the density and temperature are high enough, the hydrogen starts fusing in helium into the core of the star, and the star starts shining. The most massive stars, though, begin to shine while the clouds are still collapsing. Their ultraviolet light ionizes the surrounding gas and forms a nebula with temperatures approaching 10,000 degrees Celsius. Now, simple computer models, would suggest that at this stage, the gas around the massive star will quickly expand into what's called an H2 region, a bright emitting nebula, and the cloud dissipates, and that should stop the process of growth. So you would think there's this upper mass limit to stars, but we've seen stars. We know that there are stars out there in binary systems. We can measure their mass by their orbits, and we know that there are extremely massive stars out there, 60, 100 times the mass of the sun. So what's going on? Well, observations show instead of large H2 regions around these massive stars in nebula, instead we see several relatively small H2 regions. So recent in-depth computer modeling has shown that this is because the interstellar gas around the massive stars doesn't fall evenly onto the star, but instead it forms filamentary concentrations because the amount of gas is so great that gravity actually causes some of these filaments to collapse locally, and then they would spiral in like gas tornadoes of extremely dense gas, and they're shielded then from the ultraviolet radiation of the star, so they don't evaporate. So they went and looked for this. It was a 23-year-long experiment. The researchers used the VLA observations of the Sagittarius B2 region, which is near the heart of our galaxy. These observations were made in 1989 and again in 2012. There are many small regions of ionized gas that you can see here, these red nebulae. They're providing a large number of candidates for flickering. So over this 12-year period, 4 of the H2 regions actually significantly changed in brightening over that such a short time period. So this tells us then that these collapsing clouds are very clumpy, and also provides a mechanism for these observed very large stars to form. Go to the next one, please. The second story I have is looking an image from the Hubble Space Telescope. It's finally uncovered the long-suspected underlying population of galaxies that produce the bulk of new stars during the universe's early years. This is one of the reasons they're building the James Webb Space Telescope, is to investigate these early galaxies which caused the reionization of the neutral medium in the universe and made the universe go from opaque to transparent. So Hubble's done some deep exposures around a galaxy cluster. This is a major foreground galaxy cluster, Abell 1689. And you can see in the circles there's a lot of background blue dots, and they're blown up in the images at the side there. These are actually galaxies far, far more distant than this foreground galaxy, and they've been gravitationally lensed so that they're visible to the Hubble Space Telescope. These 58 young galaxies were photographed as they appeared more than 10 billion years ago, during the heyday of star birth in the universe. The newly discovered galaxies are 100 times more numerous than their more massive cousins, which were the only ones that you can see without the help of this gravitational lens. They're also 100 times fainter than galaxies typically detected in previous deep field surveys of the early universe that did not use these lenses. The cluster, the foreground cluster, is so massive that it actually magnifies light from these stars like a kind of a distorted cosmic lens, and allows us to see these. So the light from these things are going across the universe, and the gravity from this cluster refocuses the light back towards us. And it actually distorts the images of these galaxies as well. So we can actually get some information on their shape because they're actually stretched out. Otherwise, you wouldn't be able to resolve them. They'd just be single pinpoints. But because they're stretched out, we actually get some shape information, even though they're a little bit wonky due to the quality of the galaxy lens. Based on this data, astronomers think they actually have a relatively complete census of the galaxies behind this cluster, and that there's no sampling cutoff, as it were, to the dim end of these galaxies when the universe was only 3.4 billion years old in this area. And based on this data, 80% of new stars in the universe were formed in these small galaxies rather than the larger ones that we'd seen before. So uncovering these galaxies helps to bolster claims that the hot stars in these small galaxies pumped out enough radiation to reionize the universe within the first billion years or so after the Big Bang. These objects obviously don't look like galaxies that we're used to in the present, used to seeing nearby, like we were seeing just recently from Gary Boyle. The Hubble analysis shows that these are small, irregularly shaped objects measuring just a few thousand light years across. Even when fully mature, these galaxies will be about 1/10 to 1/100th the mass of the Milky Way. But because they're undergoing a firestorm of starburst, we can actually see them. Their ultraviolet light has been redshifted into the blue, and we can see them. This is the Hubble telescope, WFPIC WFC3 is imaging these things. So a very interesting confirmation of something that's been suspected about how galaxies formed in these very small galaxies, which then coalesced over the age of the universe to the larger galaxies that we see now. That's all. Thanks.
All right. Next slide, please. All right, one of several special presentations tonight. This is going to be the first in a series of presentations with sort of historical astronomy elements. I'm going to talk more about what's to be expected in March, but this is a wonderful sort of lead into the March presentation, an excellent lead in. So please welcome everyone, Monica Ferguson from Carleton University. Thank you.
Hello everyone, my name is Monica Ferguson and I am a map specialist at Carleton University Library. I'd like to thank Janet Tulloch, Mike, Chris, and Tim for letting me take you on a brief cartographic tour of the cosmos. So, maps are artifacts. They're documents given shape by man. Each map gives clues to current events, cultural ideas, or key processes. In this brief cartographic tour, a selection of old maps will be presented. And while maps are artifacts, they're also works of art, which only enhances the richness of their legacy. As children, we didn't likely know much about our world beyond the boundaries of our home. We'd lie on the grass and look in the sky, wondering what lay beyond. Throughout history, mankind has tried to understand how we fit into this picture. It's all about perspective, looking out to the heavens or looking back toward the land. It may be difficult to imagine the enormity of the universe, but many ancient cultures attempted to describe themselves in relation to the heavens, often with remarkable insight, but sometimes with childlike interpretations. Aztecs used celestial maps for their sophisticated calendars. Egyptians aligned their buildings according to the movement of the stars and sun. Babylonians and Syrians used tools to measure the angles of shadows on the sundials. The ancient Greeks asked, how does the earth fit relative to the heavens? This was the study of cosmography, or the study of the universe. In the mapping world, there are large-scale maps and small-scale maps. Imagine you're looking at Google Maps. Zoom in, and you've got a large-scale map. Zoom out, and you've got a small-scale map. These are the maps that help us imagine a universe. The Egyptians were connected to their gods. They looked beyond the earthly realms to help explain their view of cosmology. In this map, Nut, the sky goddess, arches over Geb, the earth god, with Shu, the god of air, between them. There he is. Maps depicting the journey for the deceased to the afterlife have also been found in Egyptian tombs. The Greeks were also interested in the heavens, but in a different way. They used their math and science skills to help map the universe. Aristophanes' map expanded the world's known boundaries, and he devised accurate calculations of the Earth's equator. No discussion of cartography is complete without the mention of Ptolemy, cartographer and astronomer. He wrote Geographia Tetrabiblos, the basis for modern-day geography, and Almagest, a must-read for ancient astronomers. Ptolemy's writings provided the basis for many maps throughout history. He placed Earth at the center of the universe, with 5 planets encircling the Earth. Here, Homer imagines a world encircled by an ocean. The world sits on a plateau atop of a mountain. Hades and Tartarus lie just beneath the Earth's surface. This 3D image helps us imagine the sun, moon, and stars rising from the waters at the edge of the dome each morning, then moving across the sky to sink into the sea each night. This clay tablet is one of the oldest maps ever discovered. It's special because even though the Babylonians were skilled at mathematics and sciences, they usually made maps for practical purposes, such as wayfinding, and not of the cosmos. On this tablet, the circular world is ringed by water. Babylon is at the center. 7 small interior circles represent cities. 7 or 8 triangles represent islands, which link the earth to the heavenly bodies beyond. The Babylonians used this cosmological map more for earthly predictions than anything else. The Romans were a military powerhouse, always on the move, and like the Babylonians, interested mostly in mapping the earth and not the heavens. In this image of the Roman world, or orbis terrarum, the sphere shape is flattened into a 2-dimensional disk. The Romans' legacy lies more in the advancement of large-scale maps or road maps, the most famous being the Putinger table. The Putinger table is one of the first road maps ever created. The map is on an elongated strip of parchment, only 13 inches wide and 22 feet long. This means distances from east and west, or in this case, top and bottom, are compressed, while the length from left, which would be Great Britain on the left, to the Mediterranean on the right, is expanded. This map provided a propagandist picture of the Roman Empire, proving that all roads lead to Rome, which of course is at the center of the map, though in our image it's at the left, because this is only a tiny section of the table. For many years, it was observed that the sun revolved around the earth. At least that's what Ptolemy thought. In this 1568 map by Portuguese Velo is based on Ptolemy's writings. On the left, Velo notes the distances of the celestial bodies to the center of the earth, and on the right, the times of the revolution in years. In 1540, a German named Peter Apian again depicts the cosmos using the 1400-year-old Ptolemaic system. Using hand-colored maps and movable paper parts, Apian describes the mechanics of an Earth-centered universe. Within a few short years, however, both of these geocentric maps will be considered out of date because in 1543, Copernicus reveals evidence that the Earth and planets actually revolve around the sun. Following this reveal, there is an outcry because it contradicts religious beliefs of the time. Eventually, Copernicus's theories are validated by Kepler, Galileo, and Newton. About 100 years later, René Descartes comes up with his mechanical philosophy, where the universe works like a continuously running machine set in motion by God. There is subtle matter called plenum, and the planets caught within this plenum move around the sun like whirlpools. This is a working model of the universe invented by the Greeks, called an armillary sphere. It's made of a series of rings which helped explain how celestial objects moved around the Earth. At first, the Earth is at the center, but eventually the design is reversed so that the sun is at the center. So there are always different ways of looking at things. In 1481, Conrad von Mecklenburg shows us his universe without circles or spheres, but rather using strata. Each layer separates the earth from heaven, complete with saints at the top. This Chinese worldview of the cosmos from the ancient Chinese concept of change divides the universe into yin and yang. Everything can be understood using yin and yang, which affects the movements of the stars, human bodies, foods, music, ethics, time, and so on. The Smithsonian Buddha is really a guide to the cosmos in the form of a life-size sculpture. The ornate details depict a conceptual map of Buddhism's 6 realms of existence. The sculpture may have been used as a religious teaching tool. Ethnocentric maps. It's all about me. The Korean Chunhando is a manuscript world map from the mid-18th century. It's surrounded by rings of mythical lands and suggests that the Earth is flat, a traditional Korean concept at this time. In medieval times, Christianity flourished, and many mapmakers were church scholars who created mappamundi, or sheets of the world, based on a TO model. In the TO model, the O is an encircling ocean, and the T is formed by the Nile and Don rivers. Europe, Africa, and Asia are clearly marked, though Asia is depicted as much larger. East, or the Garden of Eden, is at the top, Jerusalem at the center. This map uses images from the Old and New Testament residing outside the earthly space at the top. A Byzantine floor mosaic in Jordan, the Madaba map, is the oldest map of the Bible land known to survive. Largely destroyed in 746, the mosaic was rediscovered in 1884. Jerusalem is at the center of the map and is intentionally much larger in scale than the rest of the map. Originally 21 by 7 meters, its reconstructed size is 16 by 5 meters. It may have been used for holy pilgrimages, as it pays significant reference to important religious locations. A Muslim cartographer named Al-Idrisi created this world map, positioning Earth at the center of the universe, and is again based on Ptolemy's writings. Mecca is at the very center and is oriented south, the map is oriented south, which places Arabia at the top above Europe. World exploration during the Age of Discovery shifts map makers away from religious teachings towards geographic accuracy, as seen with the Waltzay-Muller map. This map shows the realization of a new continent. It's the first printed map to cover 360 degrees longitude, or the full circumference around the world. And it also shows Pacific as a separate ocean. Incidentally, it is the first map to label and name America, honoring Amerigo Vespucci's discovery. During this period, there's renewed interest in the exploration of the earth, the heavens, and in art, as is evidenced in de Witt's celestial map. During the Age of Discovery, the production of celestial globes takes off in Europe. Unlike flat maps, which require distortion or a projection to portray a three-dimensional Earth, globes are the perfect model for studying the cosmos. Change in our world today is picking up speed. Very soon, this 1999 National Geographic map of the universe will be an artifact to those in the future wondering how we imagined the cosmos. Thank you.
Now, before you go, Monica, maybe you could, Monica brought us some maps with her. Maybe you could say something about the maps, and we have also some time for some questions if there are questions.
Certainly. So yes, I have the privilege of working in a wonderful map collection that has been crafted for well over 45, 50 years and has some lovely specimens. So I brought them along to give you life-sized versions of some of the maps that you've seen today. It's kind of startling to see them actually not on a screen and on a table because, for instance, the Babylonian map, which looked pretty darn big on the screen, is actually accurately portrayed in the photograph right next to there. It's about maybe as big as my hand. So it's quite a different scenario when you're looking at the real life thing or an enhanced image. The Peutinger table is at the front, and it's again kind of startling to see well, it's not even 22 meters, but to imagine how it would have looked to have carried this scroll on your side as you're traipsing around Rome. But this representation gives you a feel for it at least. And I've sorted selections. There's one of the Madaba map, the TO map, just an assorted selection. And of course, some of the beautiful atlases and cartographic reference that we have in our collection that helped me cobble together my presentation today. So please, I hope you take a moment to enjoy some of the images that you see on the table. And any general questions?
Any questions from one right at the back?
According with the invention of the printing press, do you find any significant changes in the way maps were drawn to be printed?
Can you repeat the question, Monica?
Well, has the printing press affected how maps have been represented? And that's an excellent question. I don't have a perfect response to it, but I can assume that one of the big features of it would be the mass distribution of the products, because prior to that time, you'd only, for instance, the Peutinger table would not reside in everyone's living room. Very few people would have access to it. Of course, during medieval times, only very, very select people would have the opportunity to see the Mappa Mundi. They would be kept very cloistered in the churches. So I would think accessibility would be the biggest change. So no doubt that would be the biggest influence. But excellent question, and I'll look into that one.
Yeah, Mike, I'm just regarding the Roman map you showed there. Was there any record of anywhere in the Roman Empire that they thought the world was round, or did they always think it was flat?
Can you repeat it again?
Did the Romans, in essence, conceive of the world being round, or did they always think it as flat? I cannot speak definitively. Actually, Janet might know more to this one, but
I was going to say, definitely round.
round.
Round, and there's even three-dimensional models and sculptures showing the world as such. So they didn't have it fully mapped, of course, but they certainly had a conception that it was round, just like the rest of the cosmos.
the maps that we see, the two-dimensional aspect comes again because they are focused more toward the Earth as opposed to looking outward at themselves and imagining themselves in relationship to the bigger whole. So that's where the flatness or the two-dimension comes in. But clearly, I guess, round is part of their vision, yes.
I've heard that the modern map, the map that we know today of the Earth, is not very accurate and that it's being called a Eurocentric map. Would this be true?
Well, I have the pleasure of working with many different visions of the world. We have a whole drawer full of maps with different projections, and so that's the beauty of when you take a three-dimensional object and you flatten it, you have to distort it some way. So there's been many different reactions to how that distortion occurs, and of course with Mercator we get this equal area projection where distances on the map are well measured for the sailors who used them back and forth during Columbus's time. But strangely enough, that one projection carries through to our modern days, and largely many of us in our childhoods who had maps on our bedroom walls were familiar with only the Mercator projections. So and unfortunately, when you make the waters equal area and measurable, you make the land in what we know today as developed countries overly large. And in reaction to this, for instance, in the 1970s, a man named Peters decided that was wrong and that he wanted to stretch the world in a different way. So he created a projection that stretched the countries in the equatorial regions disproportionately. But that was great for those who want to show information on the equatorial belts because it's got nice space to be able to do so. The thing about maps is that they are very manipulable. You're able to tell stories with them based on how you use them. So they can be very good for propaganda or other tools. We have maps of Australia being at the top because they got fed up with being on the bottom. We have maps where it looks like you're standing on the cusp of the Mediterranean looking over towards Europe. Again, it's all about perspective. So yes, we have many different projections.
Are these all maps from the Carleton collection?
Not all of them, and some of them reside within the books. I had wanted to bring as big a sampling as I could, and I brought a dozen. Increasingly, as you can imagine, there are fewer distributors for maps, and what used to be a really big part of my job, which was the purchasing, is ebbing away, and so now I'm resorting to providing teaching tools through digital images as well. But if we don't have it in a large print sheet, it's likely to reside in an atlas.
Okay, one reason I ask is that I noted that this is a presentation on maps of the cosmos or the known world, but the maps of the cosmic microwave background radiation that we have are not part of it. And is that for any particular reason, or you just never thought to include them?
Didn't think to include them. Not part of my daily realm, I'm afraid. Yeah.
The other day, History Channel did a full 1-hour report on a disputed map that shows that the Vikings got to Newfoundland and North America hundreds of years before Columbus. And around the world, cartographers are arguing as to whether or not the map is genuine. And it does appear that the Vikings did have the ability to come to North America. What is your opinion, if you know that map? Do you have an opinion on it, or what would your thoughts be?
Monica, could you repeat the question for the folks on the internet?
There's been a recent discovery of a Viking map, and is it, in my opinion, likely that that could be the case, that the Vikings had discovered the Americas well in advance of Columbus? And superficially, I would say it would be foolish to think that they didn't get here first. I don't have any proof, but I think that their skills and abilities probably preceded Columbus, I would think. I do not know that map, but thank you for the heads up, because I will certainly look into that one. So I don't have any more insight into that.
I think, Frank, go ahead.
What was
Louder, Frank?
What was Homer's view of retrograde motion?
Homer's view of retrograde motion. You've got me on that one. I'm the humble map specialist, so is anybody in the audience can do that one, or retrograde motion? Perhaps you can share that one with me.
Well, what Frank is referring to with retrograde motion is the apparent reversal of planets as they go around their solar system as viewed from Earth.
I see.
It has something to do with the relative speeds or the relative, I should say, positions of Earth.
Yes.
And planet and other planets as viewed from us. So sometimes, depending on where we are around the sun, the planet is ahead of us. Sometimes it's behind us.
Right. So.
All right.
Anything else? If anyone happens to be in the vicinity of Carleton Library, don't hesitate to come down and find me, and I'll be happy to show you anything else that might be of interest anytime.
Thank you. Okay, so before we do the observation reports, something we'd like to share with you, very special, that came up a couple of weeks ago. Bob Hillier emailed me about something that I felt really strongly we should be sharing. I was going to send out an email, but I thought, no, Bob really needs to introduce this and share it at our meeting here. Bob, over to you.
Last fall, I was interviewed by TELUS for a marketing video. And I thought that they would show up at my place and talk with me for an hour or so. They showed up at 9 o'clock in the morning and interviewed me for 4.5 hours, turned my ground floor of my house into a TV studio, and then drove out to my observatory and then spent about 6 hours there. Overall, the entire day was 12.5 hours. And I asked them, so how long is this video? And they said, oh, about 3 minutes.
It's a good ratio.
So as much as this is a marketing video, I think they did an awesome job at capturing the reason why we all do astronomy.
At 6:31 p.m. on January 27th, 3 astronauts training for their first Apollo flight were lost in an accident.
The Apollo 1 capsule blew up on the launch pad at Cape Canaveral.
During a full-scale simulation of their mission, astronauts Virgil I. Grissom, Ed White, and Roger Chaffee died in a flash fire.
As a 10-year-old, I saw these guys as being real heroes. And it absolutely captivated my attention, and I've been interested in that ever since that time. I've had small telescopes, and I was always in the city when I was trying to do my observing. And the biggest challenge with observing in the city is the light pollution. So I was always interested in getting out into the country where the dark skies are, where I could get much better views of the night sky. I designed this observatory structure, and my nephews helped me build it. I decided that I could go after exoplanets, that is, finding planets around other stars. Hopefully, if I'm successful, I find something that I can report to the astronomy community and share that way. Observatories are not heated. They're not heated because heat causes the air to waver, okay, and it would create a heat bloom going up in front of the telescope. It's black, it's dark. Typically, I'm all by myself, and it's cold. Not a lot of fun. So if you can do remote observing from a warm room, that's ideal. So I just looked at, over a number of years, different pieces of software that I could bring together that would allow me to do this kind of remote access. I actually went to my local TELUS store and talked to the guys there and said, so what kind of solutions does TELUS offer? And they told me about the Smart Hub.
The Smart Hub is a wireless device with a SIM card, and you can take it anywhere you want, and it provides data.
It worked really well for the observatory to connect out to the internet, but it still presented a number of challenges for me to connect back in. I never resolved to calling tech support because I figure I can resolve just about anything. But I called them, and the first level guys decided that they were unable to help me, and they passed me off to the tier 2 support.
At that point, I tried every scenario troubleshooting we can try.
He said, well, call me back tomorrow night. I'll do some research and see what I can do to help you. So when I called back the next night, he had all the answers.
Bob had a unique case. This is actually a remote site, right? Like in the woods or something. So I figured out the solution was you need a VPN access bundle in order for him to connect to it.
He said, here's what you need to do. So he walked me through, we set it up, we tried it out, and it worked. I can load an automatic imaging run into my observatory equipment, and I turn the automated control over to the computers. The imaging run, the computers will open up the dome, turn on all the equipment, it'll autofocus the camera, it'll then position the telescope at that particular object and take an image, and it'll go off and take all of these pictures. And after it's all done, then it will shut down the equipment.
Maybe my resolution is supporting him to continue to go on.
Oh, for sure, I dream that I find something that contributes significantly to the scientific community. I think the odds are low of that, but it doesn't stop me from trying.
Hopefully he finds what he's looking for.
Okay, next up is the observation reports. Sylvie and Paul and Gordon, I believe.
Good evening. Can we have the first slide, please?
Yes, sir.
Okay. M42, nothing spectacular. I did this more as a record because I'm hoping that there'll be a clear night when I can actually get out to a dark site and compare this with my view from my light polluted Orleans backyard. Next, please. And I'm sure we'll see more of these. The supernova in M82. Gary stole all my thunder and told you all the information about it in his report, so won't say too much.
Sorry.
That's okay.
No, you're not.
That's it. Thank you.
Sylvie?
Oh, thanks. Okay, you could have put Paul's name the same font as mine. Story is, I do have a telescope in my backyard, which is not used. And I've tried in the past to use my Nikon D80 and take pictures of the moon, and I was not successful. We're not sure if the problem is the scope, the camera, or the operator. So what I did is I went to Paul's place, used his 11-inch scope, put my camera on it myself, and tried to take pictures. And before the clouds moved in, and they were moving in quite fast, we managed to grab 4 shots that we stitched into this mosaic result here. And I don't think the problem is the camera or me. So we'll have to see if my scope has any issues, but I never could get anything that good. But big thanks to Paul for proving that at least there's some part of the equipment that works. So yeah, there's my first observation and first photo astronomy picture. That's going to be the work of Chris Theron. He said he was going to put a happy face in each crater. Well, I guess he just put one big happy face.
Thanks for being a sport. Okay. Tim, next slide, please. Paul.
Hi there, everybody. Did manage to get out and get an image of M82 with. Oh, thank you. I assume that it works the same as our other one there. Yeah.
Don't assume anything.
Don't assume anything.
Not tonight.
Yeah, like the laser. That doesn't work. Anyway, it doesn't really matter. Don't really need it. This pair, just wanted to throw this in. I actually shot this pair a couple of years ago, M81 and its companion M82. The reason I include this is because M82, which is the galaxy up at the top left that has the supernova in it, not in this image, of course, but M82 is a bit of a tortured soul as galaxies go. It's classified as an irregular. It's probably a spiral, but about 100 million years ago, it had a close encounter of the worst kind with M81, which M81 being much more massive than M82, tended to disrupt the structure and just shake and bake everything up in the core. So you can see M82, there's a lot of action and irregularity in that galaxy. I should highlight the one there. Actually, the next one there, Tim, there is just the box there. Yeah, so that's the subject of our interest there. As they pass close together, these types of galaxy interactions are very common. Usually the least massive of the galaxies tends to suffer the worst for it, and eventually, like us and the Andromeda galaxy, these guys will dance around each other for a while and eventually merge into a much larger galaxy. But in the meantime, before all that good stuff happens, yes, on January the 21st, we had a supernova. And you can see it there. This is a close-up view I shot on the 29th of M82. This is, as Gary said, it's a type 1A supernova, which means that it's part of a binary system. In other words, we've got a white dwarf doing an orbital dance with another star, perhaps a more massive one. We're not really sure what the progenitor star of this of the supernova is just yet. But as the white dwarf orbits around its companion, it draws matter off the companion, sort of gets hungry and slurps this material off the larger star. Eventually, it overloads itself. It's like pigging out on hydrogen and helium, and its temperature increases, its pressure goes up, and all of a sudden it just has too much. So it blows its top, and all the other stars, of course, that you see in this image are stars within our own galaxy, except for the supernova, which is 12 million light years away. So it gives you an idea of how bright these explosions really are. I mean, this one star, this detonation of this one star, is brighter than than anything else in the galaxy out of a singular star. So current projections is that it peaked at magnitude 10.5 on January the 31st. I shot this 2 nights before the peak, and but apparently, by all accounts, and from what I've seen on the net, it's still quite bright, and you should get out a chance and have a look at it. It is very obvious, even through a small telescope. If you can find M82, you will find this supernova, and it's a treat to see. When I first saw it, it almost knocked my socks off because I couldn't believe how bright it was. I was expecting to have to hunt for it visually, but it's very, very obvious. So a really nice sight, and the closest of this type of supernova actually in about 3 or 4 decades, I believe. So yeah, interesting. Get out and have a look at it while you can. Thank you.
Okay, next slide, please. Okay, another special presentation tonight. Francois Marshall, as I mentioned earlier, is a physics student at Carleton University, completing his master's, and in the final, he's working on his thesis. Extremely busy. So Frank, I really appreciate you doing this. I know time is limited for you, so I appreciate you sharing this. Everyone, please welcome Frank Marshall.
Okay, so thanks for having me. Today I'm going to be talking about the Curiosity rover. Now, the Curiosity rover is an impressive triumph of Mars exploration. It is studying a planet in Mars which has showed contrasting fortunes in terms of our beliefs about this planet in the past few years, ever since we started exploring the planet in detail in the 60s. We've always been confronted by bouts of enthusiasm, of optimism that this planet can hold life, only to be dashed by the results of certain probes, certain rovers which have provided negative ideas to the contrary. So Curiosity is no different. It provides us with some very interesting results, like a habitable environment in the past of this red planet, but it also provides us with a whole bunch of information which is less nice and makes it difficult for us to inhabit the planet in future ourselves. So next slide, please. So first I'll talk about the history of Mars exploration. It'll just be a quick review. I'll discuss the purpose, the location, and the landing of the Mars Science Laboratory, which is what we call Curiosity. And in fact, it is a laboratory. It's a caravan. It's the size of an SUV. And it's amazing that we've landed something like this on the planet. We've never had this kind of understanding of another world. Well, in particular, I'm interested in one of the detectors on board, because this thing has a suite of instruments. The instrument that I'm keen on is the Radiation Assessment Detector, RAD, which measures cosmic rays on Mars and considers things as different as AGNs to atmospheric conditions on the red planet. So RAD consists of a charged particle telescope, scintillators, and there's a really interesting electronics board, but I'll see how much time I have before I can describe that. And finally, I will discuss one of the most important results we have gotten from this mission, which is it's dangerous to go to Mars, and there are particular reasons that we didn't know about before. So next slide, please. So exploration of Mars began in earnest in the 60s when we sent Mariner 4 and Viking 1 and Viking 2. So bunch of satellites, bunch of landers, and we wanted to know particular information about a planet which to us was still misty. We didn't have a great idea. In fact, when we sent Mariner 4 to the red planet, we had an idea that it had vegetation in its southern regions. So clearly when we got feedback from Mariner 4, this was during the space age, of course, it was a problem because we found that Mars was actually an arid desert. It wasn't as far off, it was quite close to the moon. So people were very disappointed. They expected to find Schiaparelli's canals, the irrigation systems that had been set up by an advanced civilization of such superior technology that we were even scared they would colonize the Earth. Of course, this was a bit of a misunderstanding. Canali means channels. People thought canali meant canals. Unfortunately, this led to a popular belief that Mars was a lot more advanced than we had anticipated. So this information certainly bogged down our expectations of the planet. And when we sent Viking 4 to collect samples of vegetation, we didn't see what we wanted. So next slide, please. So here's some picture of Viking 1. It landed in an area called Planitia, the Gold Plain. And you'll notice, and this is in the northern hemisphere where everything's very flat. You can see here a variety of different boulders, of different rock formations, and this is a result of water. We could tell that water had probably laid on Mars for quite some time, ever since we really landed things there. So you can see that there's a whole different variety of boulders. You've got aeolian features where erosion has occurred because of winds. You can clearly see dune-like formations in the background. Next slide, please. So, sorry, it's a bit blurry, but here's a picture taken by the Viking 2 lander, which landed in Utopia, Planitia, near to the other side of the planet. So it's still in the northern hemisphere, but we had this idea that this would be a good opportunity to get some plant samples. Obviously our understanding of the planet has much advanced since the 60s, because now we know there's nothing of the sort on this planet. And of course this is an igneous region. It's not as impressive as the previous one, which seems to have been formed by sedimentary processes. Next slide, please. Here's a really nice picture I find. It's from one of the orbiters. And you can see in the middle here is Elysium Mons. Now, what's really impressive about this is that you have a bunch of streamlines. And this is stuff we knew as early as the 60s and the 70s. We knew that there was probably water on this planet. And the reason it's interesting is because you see these huge streams, these outflow channels, where water that was before part of the permafrost was heated by plume activity and warming, and the permafrost turned into groundwater. The groundwater seeped out in vast amounts, and we ended up with catastrophic flooding. So this is just one example. Next slide, please. Here you can see more catastrophic flooding. You can see the channels clearly going around a crater. So sometimes craters would navigate where the channels went. And you can see that this crater has a particularly high rim, so it's quite obviously navigating what's going on with the channels. It might be because I was pressing the bottom. So,
Oh, yeah, that'll
yeah,
do it.
that probably. So next slide, please.
Yeah, you were getting the,
Yeah, I just realized. Yeah.
yeah, there's a button in the bottom of the blanket.
So here's another type of feature we found on Mars, which suggested that there was water on the planet. These are called runoff channels. This network of water this network that forms a water system, you can see its dendritic appearance, and that's associated with mainly rainfall, I think, as much as anything else. Rainfall that stays and has an impact on the surrounding groundwater, therefore creating a whole series of channels. It's a lot more random than what you see with an outflow channel, where the flooding is much more catastrophic. But you can see that there are all sorts of different features on Mars that we already knew were suggesting that we were looking at a once wet planet. Next slide, please. So we had sent a bunch of rovers and probes to Mars, a bunch of satellites. We'd gotten some information about the planet. We were trying to do everything in a hurry. We kept looking for vegetation, for life. We were looking for everything in one. We were sending an all-in-one mission every time. This was a space race. We wanted to impress the Soviets. We wanted to find life on Mars straight away. By the time of the 90s, we hadn't sent many probes there for quite some time. In fact, there was a 17-period gap in which we didn't send anything at all to that planet because our enthusiasm had plunged. We really did not have the same expectations of this planet as we once had, and so it seemed like a boring world like Mercury. This is even knowing that they had volcanoes. These images I showed you of volcanoes like Elysium Mons, we knew that. But it seemed not much different to it seemed like a glorified version of Venus or Mercury or the Moon. So we weren't very interested in it. But there was this evidence of water, and it still lingered at the back of people's minds. In the mid-90s, having seen a series of failed missions to Mars, including one which cost some $1 billion, go up in smoke, the Mars program decided to appoint two different people, Scott Hubbard, the program director, and Jim Garvin, the Mars program scientist. And these two people completely changed our approach to how we went about understanding the planet, about how we sent things there. Rather than the ambition, rather than the speed at which we were going to understand this planet, we had to understand that this was an entire world. It was like studying the Earth in a way, because there might not be oceans, we might see most of what's there, but there are so many secrets hidden underneath this surface and over it. And we just don't know half of what's going on. All we know is that Mars is probably not as exciting as we think, but there are a lot of secrets that it can provide which can help us understand the planet as a once habitable zone. So this is what they did. They sent two rovers, which you can see bottom, Spirit and Opportunity. They sent Mars Odyssey. They wanted ground truth here. They wanted a survey here. And the net result of this was to understand the Martian geology, to understand where you might expect to find water, and these two provided ground truth for those surveys. So, next slide, please. So this leads us to 2012. Now, Garvin and Hubbard as early as 2001, had it in mind that they would send Sojourner. They had already sent Sojourner to Mars, but this was part of a wider plan. They had a long-term vision of what they wanted to do with this planet and how they wanted to go about understanding it. So what they did was they knew that they had the geology understood to some extent with Sojourner. They'd landed a rover successfully. It had done what the Viking landers couldn't do, which is move around the environment and take particular samples of interest in the local region. It had sent 2 other rovers which had traveled long distances, understood the environment really well. And this was all going to plan. And in the 2001 article that I read of Astronomy Magazine, they said that they expected that as early as 2011, we would have a great rover on Mars that would pick up a sample and we would use it as a return mission. We would actually bring back some of the Martian soil. So first of all, we didn't land anything in 2011. There was a few problems along the way. Secondly, we changed the outcome of the mission, and instead of sending a sample return mission, which we might do eventually, we ended up sending a caravan to Mars, an SUV. So it was light, and it wasn't a sample return mission. But at the same time, we have an extraordinary object on Mars, a really brilliant piece of engineering. So next slide, please. So here's a map of Mars. And what I want to talk about is the Martian dichotomy, because this determines where we're going to land this object. What is interesting about Mars? The dichotomy of Mars is represented along the equator, essentially. And the reason that this is because the reason there's this dichotomy is that you have the southern highlands and the northern plains, which are much further down. They're much more boring in terms of the amount of topological differences. And of course, they have the volcanoes in them. So it's a mix. But what's interesting about this dichotomy is that with the southern highlands, you have lots of areas where there could have been water near the equators. And if the water starts to flow, if you have outflow channels, catastrophic flooding, it's easy for the thing to go down slope. So here you can see some outflow channels that were seen by some of the earlier orbiters. Next slide, please. So why do I talk about the outflow channels and that dichotomy? Why do I talk about the intersecting line that is an escarpment? It's because of where we land our rovers. Look at where Viking 1 lands. Look at where Viking 2 lands, near a green spot. Look at Curiosity and Spirit, Opportunity, the Pathfinder, all the familiar names. They all occur where the topology goes from high to low, because that's where the easiest access of the water that might have left here to end up in a puddle. Or in this case, something more impressive, which could be like a lake or even a sea. So the water would have gone from this high elevation, landed in here, and maybe formed some kind of water body. And it's because of this opportunity of deposition sites that we land all these rovers along the dividing line that forms that dichotomy. Next slide, please. So here you see the water concentrations as determined by the Mars Odyssey survey that was done earlier in the millennium. We have large abundance of permafrost, or should I say hydrogen content, around these regions near the equator, close to the dichotomy. We have a particular excess of hydrogen-bearing compounds in the poles, and that's expected. These are where the caps are. So if we're not going to put it near the caps, because nothing probably lived there, it was too cold at the time, let's put something along the equator where we have a better chance of something happening. Next slide, please. So this is the promising environment that John Grutzinger, the project scientist of the Curiosity rover, and his team decided would eventually be the final landing site. Now, it wasn't exactly their decision as such. They had hundreds of scientists working on it. They came up with several sites. Some are more impressive than this, some more boring, but more flat. It was a compromise. It was a compromise between the engineers. They wanted to get some data. They didn't want their expensive rover falling off a cliff. So they wanted something flat. But you also had the scientists, on the other hand, who said, we want something interesting where we think there might have been life. So here you can see the beginning of the main mountain at the central uplift in Gale Crater called Mount Sharp. This is a stratified entity about 5 kilometers in height, and you can see that Curiosity landed in an ellipse here where there was an alluvial fan, which is a sediment region, deposition region that is associated at the mouth of an elevated geographical object. So next slide, please. So a lot of us will have seen this. This is an image taken from the video of the landing of the Curiosity rover on the Martian terrain. So, of course, this was a very impressive landing. You were talking about landing an SUV on Mars, essentially. A whole suite of instruments. You don't want any of those to get damaged. So you need the landing to be soft. But at the same time, you're going in at a fast rate, coming in. You have very little atmosphere to stop you. So the parachute won't do all the way. You need to get rid of the rover fast. You had 7 minutes to complete the entire process. You want protojets to keep this thing stable as it's landing. So it's a very slow landing. The top part moves away. It doesn't want to land on top of the rover and crush it. Next slide, please. So here's an image of what Gale Crater looks like, the region of landing. Here's the landing ellipse. It wanted to land, I think, around this area near the center, which was an area called Bradbury Point, after the famous Ray Bradbury, who passed away only a few years ago. You can see the alluvial fan, and Curiosity landed a little bit away from Bradbury Point. So they've landed there. There's Mount Sharp right in the distance, this layer of strata, this potential that can tell us about the history of Mars, layer by layer. The rover is going to climb this thing up to about halfway. It's going to tell us a lot of information. So once it lands there, what does it do? It goes the other way. So the reason it goes the other way is it goes half a kilometer one way, and then it's going to go 8 kilometers the other way. The reason is because we've got 3 regions. I don't know where it is here, but you had 3 intersecting regions of geology, different types of terrain. And these types of terrain, at their intersection, at their junction, they form a composite geological feature called Glenelg. So it went there, got a lot of information. And it was on that path that it drilled into John Klein, the first rock sample that it got information from, where it determined that there was a once habitable environment on Mars. It successfully accomplished the minimum incentive of its voyage. Almost straight away, it worked out that there were sulfide, phosphates, different types of compounds that were essential for life that could be found in one of the elements, just almost randomly selected, really. So it found a ton of information from its detectors straight away. Next slide, please. So this is the rover. It wanted to find if he had habitable Martian environments. It has a suite of instruments. So we have one called RAD here that I find of particular interest. The mass cam's important. It looks at things at a distance. SAM's important because that's the one looking for organic compounds. That's the one you hear about in the news all the time. But RAD I find was really interesting. So next slide, please. So just to tell you a little bit about RAD, I'm not going to take too long on this, but because of time restrictions. But the idea is we want to see what happens if we take a round trip to Mars. What kind of radiation dose do we expect? And it tells us about whether the planet might have been inhabited earlier on, or if the radiation dose on the surface was too high. So next slide, please. So cosmic rays come from 2 different sources in particular. One is the sun. It comes from coronal mass ejections. It comes from solar flares, high anomalous regions of magnetic activity. Next slide, please. Another source of cosmic rays is AGN's active galactic nuclei. You see streams of protons being ejected and also heavier elements like iron-56. So next slide, please. When these 2 sources of cosmic rays emit protons, so say 90% for cosmic rays, all protons for solar energetic particles, and even heavy ions like iron-56, they interact in the atmosphere and they produce showers in the Martian atmosphere. And this they can also produce neutron reactions as the cosmic rays are moderated by this permafrost. So next slide, please. So here's a picture of the RAD detector. It has 3 charged particle silicon detectors, 1, 2, and 3. These are solid-state detectors. They tell you about the energy that is deposited by charged particles like protons. If we want to see about the neutrons that scatter, that are ejected from the surface as a result of the cosmic rays, we want to look at the scintillator down here. If we want to see about gammas and gamma rays, we want to see about other neutral particles, we can use another one here. And it's like a telescope. You have to look at it within a viewing cone of 60 degrees. So next slide, please. So this is just another image. It shows you that there's a viewing cone and particles go through these top layers and are detected here. We want to have an understanding of the spatial dynamics of this thing. So next slide, please. The rate of cosmic rays changes based on the atmosphere of Mars. For example, there's this convection system that occurs between the ice caps and the equator. And when this happens, you get a certain level of atmospheric nitrogen, water, and carbon dioxide, which might not be there during the winter, because in the winter, all that material accumulates as snow at the ice caps. So if I were standing here, which is more or less where the rover is, you would have a lot more atmosphere to worry about. The column depth would be different. The level of cosmic rays would fluctuate. So next slide, please. So these are the types of measurements we're getting from RAD. This is how much you get from a cruise to Mars, on average, the dose. And this is the dose you get on the Martian surface. You see heavy ion events. This is like iron 56 coming from cosmic rays, like AGN sources. And you can see that there's variations based on things like the heliosphere and how it blocks the GCRs. So next slide, please. So this is where I want to come to, and this is the end of my presentation, essentially. The RAD detector measures radiation. And as you do a full flight to Mars of 500 days in total, so you go there and back, you're expected to receive 662 millisieverts dose. Now, what does this mean? Well, NASA says that over the course of your entire career, you shouldn't be getting more than 1,000 millisieverts, because otherwise you have a 5% chance of getting cancer. The problem with 662 millisieverts, people won't be able to work on the planet properly once they get there, because they'll be suffering from radiation sickness, even if they might not die of cancer later on. So this is a real problem, and it tells us that we really have to change our idea of sending people to Mars, like the Mars One program, because otherwise we're going to be stuck. We need to develop our shielding. It's not going to be easy. We might not be able to encase the entire spaceship like that, so we might need a storm cell for particularly violent periods of cosmic rays. So next slide, please. So in conclusion, we have some information about this rover, which is consistent with the problems that we've had about Mars in the past. And it's not always positive what we find. It could have been inhabitable, but there's so much radiation on that planet, maybe it wasn't. And we also have a lot of trouble sending people there right now. We won't have anything happening in the near future. Next slide. So to conclude my presentation, this is a line from the 2001 edition of Astronomy magazine. Like a snowball rolling downhill, the exploration of Mars can only get larger and more exciting with time. From this momentum will naturally follow the first manned missions sometime in the early to mid-21st century. We think it looks so far so good with the Mars One missions. It might not be the case, and this is the problems that we encounter with the red planet. Okay, thank you.
We can probably take about 3 minutes of questions. Is there any questions, or Chuck?
Yeah, the mysterious rock that Curiosity found. Any ideas?
The mysterious rock. Okay, so there's a mysterious rock that Curiosity found. Is that the one that looked like a jelly donut?
Yes. Is it a spore or is it a rock?
I think it's a jelly donut. Is it a spore? Is it a rock? Can you define spore? I'm sorry, I'm not that familiar with the actual details.
Actually, the Planetary Society thinks it might be some kind of instantaneous plant that just popped.
It's not a plant. I've seen the picture. It looks like a geological object. It probably landed there while it was away through some kind of dust storm, I'm guessing, because, you know, dust storms are quite regular. The probability of having a plant just turning up, especially after it looked at that site in detail, I think it's unlikely. We have to be very skeptical about this. It's probably some unusual rock with the interior red bit being something to do with some iron mineral or some exotic mineral like the blueberries that the Opportunity rover found, that kind of thing.
Question right at the back there. Can you speak really loud, please?
Yes, thank you. We have all this evidence that in the past there was flowing water on the surface of Mars, but clearly now with the temperature, the low atmospheric pressure that are there now, you couldn't have liquid water on the surface.
Okay, so...
Does that point to some maybe catastrophic event that happened in the past? And if so, is there any instrumentation on Curiosity that would allow us to date when such an event happened, or when there actually was flowing water on the surface of Mars? Because Mars was once warmer, had volcanic activity, has the biggest volcano we know of in the solar system, especially the size of the planet.
Okay, so I don't know what the catastrophic event was, but I did read about this in the news when I heard about this idea that a catastrophic event might have caused the loss of the atmosphere of Mars. And this loss of atmosphere ended up producing a lack of water. It started draining away all the life from the Martian planet. And Curiosity's rover, SAM, the sample analysis at Mars instrument, looked at particular soil samples, and it found that these samples showed evidence of Mars losing its habitable environment, if there was any, about 4 billion years ago. This isn't very long after the planet formed, which was about 4.5 billion years ago. I'm not sure about what the catastrophic event was, but that was the instrument, SAM.
All right. I know there's some other questions, but we run out of time. You can ask Frank questions after the meeting. Thanks, Frank. Frank, you are one very impressive fellow. That was a terrific presentation. I think I'm speaking on behalf of everyone here. Okay, next up is Glenn Ledrew. Glenn, Stellar Associations of Perseus.
Well, for about the first 10 or 15 years of my investigations in the night sky, I was like many backyard telescopists, where I tended to look at the sights in the heavens more in isolation. I was interested in the phenomenology, how big, how bright, what kind of detail could I see, and I would just think of them in isolation. But then at some point I became curious about obtaining a wider picture, a fuller picture of the larger scale structure of the galaxy and how the various objects were located within it and how they interrelated with each other as well. And one of the interesting sidelines in this area is the study of stellar associations, especially the young ones where new stars are currently being formed. Young associations can be anything from, stars currently forming, and up to perhaps a few tens of millions of years old. By the time you get beyond, say, about 50 million years, these groups are no longer considered quite so young anymore. And what we find is they're usually enmeshed within the spiral arms, where the concentrations of the molecular clouds and denser gas clouds reside that stars form from. And because these are sites where we see new stars form, that's where we tend to find the very massive stars, which are intrinsically very bright. And we can see them to great distances and therefore sample what's going on over a fairly considerable part of our galaxy. More run-of-the-mill stars are much less bright, and we see them only to a fairly near visibility horizon before they're so dim they fade off into nothingness. So when we look to the distant part of the galaxy, we see the really bright stuff mostly. So we have a bit of a biased view as a result, but it's very interesting. Now I'm concentrating here on 3 of these young star-forming regions that are found in the constellation Perseus. And in fact, one of the associations is the source of the name, actually, of one of the major spiral arms in our galaxy, the Perseus spiral arm. So now we can jump ahead. Actually, I can do that right here. This is an overview from a free program you can download from the Hayden Planetarium. It's called Party View, short for Particle Viewer, and it's a 3D visualization tool. And if you're really into it, you can even customize it to your heart's content and add all kinds of database elements. And I've done some of that as well with this program over the years. This image here, it's just a photograph of some galaxy. I forget which NGC object it is, but it's thought to reasonably well resemble our own Milky Way galaxy if we can observe it from a God's eye view from a great distance away. And here we're showing a view as though looking down on the galaxy from the galactic North Pole from a very great distance, and we see our half of the galaxy. The sun is at the center of this little circular grid pattern that I created, and the center of the galaxy, of course, is down at the bottom. I'm showing also a circle, which you will see in the close-up images, that is called the solar circle, so named because it is at a distance of about 80 or 8.5 kiloparsecs from the galactic center, or the sun's distance from the center, and it helps us to distinguish what we call the inner galaxy and the outer galaxy. In this wide-angle view, we see a reasonable correspondence in this galaxy to the spiral arms in our part of the galaxy, they being the Sagittarius, which is inward from us, our own local arm, or Cygnus Orion arm, in which we reside, although we are here purely by chance. We've gone around the galaxy about 20 times since the solar system formed, and we pass in and out of spiral arms all the time. We just happen to be within this little arm right now. And then outside of us is the Perseus arm. I'm sorry, I'm hitting the button here prematurely as I'm trying to activate the pointer. So yes, the Perseus arm outside. And I've added in the known OB associations, which there are a couple or so dozen of the major ones that we know of. And I've colored them here, so it's a kind of a purpley color for Perseus, green for the local arm, and an orangey color for the Sagittarius arm associations. Now this circle here, that's 5,000 light-year radius, or 10,000 light-years wide. We are seeing some of the associations, especially in Sagittarius, to as far as about 10,000 light-years from us. We don't see very many farther than that because of the general extinction by all the dust that pervades the galactic disk. Now here we take a more close-up view so we can see the arrangement of these young stellar associations a little better, closer to our own local neighborhood. And the 3 that I'm going to be highlighting are the Perseus 1 association out in the Perseus arm, which is the source of the name of the Perseus arm. And then much closer in we have Perseus 2, about 1,000 light-years away. Perseus 1 is anywhere from 6,000 to 7,000 light-years out. And then closer still, Perseus 3, roughly, well, very nearly 600 light-years out. Incidentally, I should point out that this little group of blue-colored association symbols, while they reside in our local arm, and normally I would have colored them green like the rest of the Cygnus Orion groups, I've isolated them with a different color because these are belonging to a substructure in the galaxy called the Gould Belt, an interesting substratum of stars tilted about 20 degrees to the disk of the galaxy that's been around for perhaps 50 to 60 million years since the first generations of stars formed, and then another outburst about 30 million years ago or so when the density wave of the local arm passed through. Okay, which button did I push here?
Probably the bottom one.
I don't like this controller very much. It's too easy to push the buttons when you don't intend to.
Don't push them.
Anyway, so yes, the Gould Belt, which happens to nicely surround us. We're by chance located within it, a little bit off to one side and almost exactly within the plane of that structure as well. So now we'll move ahead here to an overview of that part of the sky as we see it from Earth. This is an image that I captured from the desktop planetarium software Desktop Universe, which is now defunct, but the same all-sky mosaic resides in the Pro version of Starry Night. The Starry Night Pro Plus actually is the version that you can see this mosaic in. And so we can see the outline of the constellation Perseus. It's tilted so that the North Pole in the sky is toward the upper right, and we're including the Milky Way band, and the galactic equator is shown with this white line running diagonally. Closer to the galactic plane, in part because it's very far away at, as I say, 6,000 to 7,000 light years, is the Perseus-1 association, which includes the double cluster. Many associations happen to include one or two open clusters as part of the hierarchical structures that make these young groupings. We'll see concentrations of star formation that result in clusters, and then a general wider distribution of unbound stars, which over time will gradually dissipate and spread throughout their part of the galaxy as they slowly disperse due to differential galactic rotation primarily. As we move further down into central Perseus, we have the Perseus-3 group, the core of which is Melotte 20, or the Alpha Persei association or cluster, which is a beautiful binocular object actually, and is even visible to a certain extent with the unaided eye. The brightest star being the brightest star in Perseus, Alpha Persei, which lends its name to that group. And then down in lower part of the southern part of Perseus is the Perseus-2 group, which happens to be the youngest of the three. It's located not far from the Pleiades, and incidentally I can say the Pleiades is not far from the core of the Gould Belt and is related to it, whereas Perseus-1, farther out, is actually out on the far side of the Gould Belt as we see it from our vantage point, and actually delineates the outer rim. It's one of the groups of new stars forming along the rim of the expanding Gould Belt system. I should also mention, and you can see in the image here, the patchiness of the extinction clouds in the galaxy. Particularly along the band of the Milky Way, there are many dark rifts and clumps of this denser molecular gas, and they appear dark because they're of higher density. All throughout the disk of the galaxy, by weight, there is about 1% of the mass of the interstellar medium is actually dust particles. The other 99% is gas, but there's enough of this dust in spite of the vacuousness of it that it can end up being a serious impediment to visibility. In fact, on average, for every 1,000 parsecs you look in through the galaxy, you've got about 1.6 magnitudes of extinction. So over great distances, anywhere you look, you're going to see the effects of dimming and also reddening on starlight. And that affects our view of the galaxy and how far we see. Even well away from the plane of the Milky Way, we'll see isolated clouds as well. Down here near the Perseus-2 group, there are many clouds which are involved with it, and some even closer to us. The Pleiades, at only 400 light years, is passing through part of these Taurus-Auriga cloud complexes. And in fact, the reflection nebulosity that surrounds the Pleiades is not related to the cluster itself. It's just the stuff that the cluster is happening to be passing through and lighting up as it traverses these clouds. So the first group we'll take a closer look at is the Perseus-3 association, which is visually the brightest, although it's fairly dispersed because it's not terribly far away from us at a little less than 600 light years. The brightest star is Murphak, or Alpha Persei, which is actually a very viable candidate as a supernova event in the not terribly distant future. It's an F-type supergiant with a sort of a creamy color cast to it, as is expected for an F supergiant. The less massive stars, you can see them here with a kind of a bluish color. These are B-type, mostly main sequence, or perhaps slightly evolved off the main sequence. Fairly massive stars themselves, but I don't think any of them are quite heavy enough, at about 8 to 10 solar masses being the limit. They're not quite heavy enough to eventually explode as supernovae. The main bulk of these association or cluster stars form a very interesting, sinuous, snake-like S shape that's very obvious when you don't include so many faint stars as I do here. In a pair of binoculars, it really stands out and is one of the outstanding binocular sights in the night sky, I say. I always revisit this every time Perseus is up and I'm looking that way. Now, somewhat in the foreground is a red giant star, Sigma Persei, not involved with this group, but it's interesting to look at because it has a nice color contrast with the blue color of these B-type main sequence stars scattered around it, somewhat in the background. Now we move a little further out now, as I said earlier, along the outer edge of the Gould Belt system to Perseus II. This includes a couple or few of the stars actually that outline the constellation Perseus, Xi Persei, Zeta, and Omicron. These three naked eye stars are the brightest Perseus II members. And in fact, Xi Persei and Zeta certainly are massive enough themselves to eventually go supernova. Now, in the past for this group, which is just a few million years old, the star Xi Persei was ejected from the main mass of the stars, which is concentrated more down in the lower part of the image here. It was ejected through space at a speed of about 60 kilometers a second and is therefore classed as a runaway star. It's flying mostly directly away from us, so it's actually somewhat in the background of this group, behind it, and it's passing through what could be perhaps some earlier remaining gas that was involved with the formation of this system that has since expanded, or if not related, at least nearby. And Xi, as it's flying away from us, is lighting up part of this molecular cloud system up here to make the California Nebula. Now this nebula is very large. The length of it along here is about 5 to maybe 6 times the size of the full moon in the sky. So a pair of binoculars will show it, although it's good to use something like high contrast nebular filters designed for blocking sky glow and helping the light of these dim nebulae to come through with better contrast. In the southern part of the association, we find near the star Omicron a cluster and reflection nebula system called IC348. For small telescopes, you can see a few of these cluster stars. It's not really a very rich clustering, but on a good dark night, you should see some of the reflection nebulosity being illuminated by these stars. And there's still remaining a somewhat tattered molecular cloud system here, and the denser parts of these cloudlets have Barnard numbers. Edward Barnard, back around the turn of the last century, before the last one, that is just around 1900 or so, began to photograph the sky with a camera of his own making, and found lots of these dark spots in the sky and created a list or a catalog of them, and we use these designations to this very day. If you're under a very dark sky with either a rich field telescope or a very large binocular, you can tell the presence of these clouds by the relative paucity of stars compared to the somewhat richer surrounds where we're not seeing the starlight being blocked by these clouds. Here's a bit of a close-up of that southern part of the association, including the sparse cluster IC348. The various Barnard nebulosities here are outlined, as was done for the Desktop Universe project, for all the Barnard objects, and a few of the deep southern ones which are not in the Barnard catalog. Another interesting nebulosity related with this is NGC 1333, one of the brighter reflection nebulosities in the sky in terms of surface brightness. With a pair of 100mm binoculars. I found this very easily one time. I only knew the general location. I didn't prepare ahead of time. And I just star hopped from Zeta to Omicron and made a dog leg down here, just sweeping along, and lo and behold, it showed up fairly obviously. I think it's a kind of an object that not too many amateurs tend to seek out, these reflection nebulosities. They're some of the more interesting objects. And what we find is reflection nebulosities very, very often are found in close proximity to the obvious dark clouds. And there is, of course, a direct relationship between these. And then just a bit more of a close-up of the California Nebula. As Xi Persei is hurtling away through space, the stellar winds blowing from it cause any nearby clouds to somewhat become compressed by the force of the stellar winds, but it's the ionizing radiation, the ultraviolet light, that causes the gas to shine. And we see it most strongly in hydrogen alpha, which gives that deep red color familiar in photographs of most nebulosities. You can see as part of this cloud the unilluminated part up here. You can see it as a bit of a darkening in the field where it's blocking the stars in the distant background from shining through. Now we look to the most distant of the associations, Perseus 1, which is, as I said, 6,000 to maybe 7,000 light years away out in the Perseus arm, and the famous double cluster forms its core. This is also a fairly young association, but we don't find any very obvious gas clouds in the vicinity. They've probably been mostly blown away and shredded, so that the even the bright ultraviolet emitting massive stars cannot light up any nearby gas because there's nothing in the vicinity. So the Perseus 1 group occupies a great portion of the right side of this picture. By the way, this view is about the size of a binocular field of view. Because it's seen very near the plane of the Milky Way, where we have a great profusion of stars, it's very hard to ferret out which stars are members and which are not by sight alone. It's just completely confusing because of the plethora of stars along the line of sight. The really obvious ones, of course, are the two clusters themselves, which are fairly rich, massive, and very spectacular objects. And we also see among them a number of red supergiants, which the next image will show. Before I get there, though, I wanted to point out that another potential member of the association is 10 Persei, which is just about on the verge of naked eye visibility in spite of its great distance. You can see in the image here some darker clouds which would lie nearer to us than the Perseus arm, maybe in the outer part of our own local arm, and is causing noticeable extinction. To the right, much less so. Nonetheless, there is general obscuration such that these clusters are dimmed by about 1.5 magnitudes, or a factor of 4. So imagine if it weren't for that, these clusters would be about 4 times brighter than we see them now. Another consequence is that with that dimming, the starlight is reddened or de-blued, so we don't see the bluish color of the stars like we normally would. They are now more like a neutral white color, therefore somewhat yellowed, if you will, because of the subtraction of blue light by the intervening dust. And here's a close-up, again from Desktop Universe, and I've toned down the sky brightness so that the stars aren't quite as numerous. And here I've also saturated the colors to help bring out the color contrast between the cluster stars. Now in photographs, even though the stars are more of a neutral white, they still tend to have a bluish cast oftentimes. But you can see a number of these nice orange glowing embers scattered about. Most of these, particularly these 6 here, 1, 2, 3, 4, 5, 6. These are known red supergiants in the association, not necessarily tied with any of the clusters themselves, but certainly as members of the general, more dispersed association. I'm sorry I keep doing that.
2 minutes, Glenn.
Yep. And actually, I do believe that's my last image. And it is. So I guess then we have a couple of minutes for questions, if you have any.
Any questions?
Well, I guess I've been quite thorough and made sure that you don't have any to ask. Great. Thank you.
I guess We do have a question?
Yeah, I just wrote a quickie one here, Glenn.
Yep.
And any insights on why the Perseus double cluster does not have a Messier number? Repeat what did Messier?
Yeah, why does the Perseus double cluster not have a Messier designation? That's a question I've pondered over the decades, actually, because the Pleiades, which is well known from antiquity, was given a Messier number, which I think purely was to round out the number when he published his first catalog back in, I don't know, 1760-something, if I recall. And anyway, I think it was purely gratuitous from that standpoint. But also the Persepi, M44, was included in his catalog as well, another object known from antiquity. The Andromeda Galaxy, I think, was also another known fuzzy smudge in the sky, which is 31. But why the double cluster? I don't know. If someone could answer that, it would help me sleep a little better at night, I think.
All right. Thanks, Glenn.
Thank you.
Okay, let's go. Thank you, Glenn. Okay, we're coming quickly to the end of the night. Just a couple of quick announcements here. Jim Thompson has, I mentioned last month that he's been sort of the heart and soul of a series of astronomy workshops. There was one held just recently, do-it-yourself mini and micro observatories. Various speakers were sharing their experiences. Wonderful feedback I heard. He's doing another presentation again, or really workshop again, where he's inviting speakers to share their favorite astronomy book and why. You can attend in person. If you do, send Jim an email. There's his email address. You can also attend virtually online. He like us. He streams the presentation online. Okay, so good job, Jim and team. Next slide, please. Okay, I'm going to say really quickly here, Astronauts is back, thanks to Janet Tillich. You're going to see an email this weekend. It'll be posted, really, on the web. We're just working on that, but terrific, Janet, for bringing that back. Okay, and next slide, please. Estelle's pick of the month. I mentioned earlier that we have a astronomy library. Just go outside the store here and turn a sharp right. Chasing Venus. That's Estelle's recommendation. Next slide, please. Okay, and closing off tonight here, just a reminder that the rest of the museum is closed. There's a group of people that you're welcome to join. There's a sort of a social event right across the street on Saint Laurent at Kelsey's. Next slide, please. There was 98 people here tonight. I understand 50 people joined through the internet. Thank you, 50 people, and those for joining. I also want to do a special thanks to the speakers and presenters. Caliber of content tonight was amazing. Okay, what you saw tonight was really a result of a real passion, and people were doing this just because they love to share their knowledge. So thank you, everyone, for some awesome presentations. Behind the scenes, there was a few people that helped make this happen. Chris Tarrant, Tim, thank you. And as always, Eric, you're amazing to be able to put together productions like this. Next slide, please. Next month, the next presentation, next meeting, it's first Friday of the month, which is March the 7th, same location. Next slide. Actually, just go back for 1 second. One thing I wanted to mention, I really cherish your feedback, okay, on what you think works well, maybe what areas we can make improvements. So please send me an email. You can send Chris Tarrant an email as well. I want to make this your meeting and one that you look forward to. So please, and also for the new members or people who are new, come see me. Let me know what you think. I want to make sure this aligns for your interests. Okay, next slide. Okay, next month. I'm really excited about next month. We got two. It's a special meeting. We've got some extended presentations. We're going to still stick within the time frame. Carrying on, as I said, with the theme of ancient astronomy, we've got Dr. Sarah Simmons from McMaster University. She's been studying the tombs of ancient Egyptians. Ancient Egyptian tombs, and looking at the walls and ceilings, and looking at the maps in those ceilings, and trying to understand how the ancient Egyptians looked at the heavens, how they mapped the motions of the objects in the night sky. Terrific speaker, full of energy, And some of you might have seen her she presented in the Science Center in Toronto with the Toronto RAC Center. I just heard wonderful things about her presentation. She's looking forward to that. Also, Simon Hamner, who we all know, full of energy there as well, and Mike Wirth are collaborating. Mike with his amazing lunar pics. Simon has an interesting presentation on what he calls polygonal craters. Okay, so what he's basically saying is we all think that there's a popular notion that craters are circular in shape. He says, in fact, that many of them have many sides, and in fact, some of them are perfect hexagons. He's going to share, hexagonally shaped, he's going to share his view, or a view, of why that is. Okay, so I think it's going to be a treat. And is that it? Okay, I'm going to close the meeting, and I'm going to run the door prizes right now, but thanks for joining online and in person here. I'm just going to call out the numbers for the door prizes, and thank you, everyone.